Hello, today we're going to be talking about binomial distributions. We're going to talk about some binomial experiments, and then we're going to talk about finding probability with binomials and normal distributions and how that works. So two different sections here going on. So let's talk about the first one, the binomial experiments. What is a binomial experiment? Well, there's only two possible outcomes, a success or a failure, heads or tails. You make it or you don't. There's a fixed number of trials. We're going to do this 5 times, or we're going to do this 20 times. The probability of success is the same in every single trial. Either we get it or we don't, and that doesn't change. It's not like we're picking something out of a bag because that will change. It's got to be the same bag over and over and over again. Each trial is independent, so one does not affect the other. And the random variable is the number of successes in a trial. So we figure out that. So let's look at the formula. The probability of success is the combination of n things x times s to the x power and f to the n minus x. So we're doing a combination of how many and our success to how many successes we want and failures to how many failures we want. N minus x, that's the amount of failures, right? Remember, success and failure should add up to be 1, but it's basically 3 things that we're going to be multiplying together. I'll show you how we do that in just a minute. Of course, remember, you can do combinations on your graphing calculator under the math button, but that's how this is done. So let's take a look at our first example. I'm sorry, before that, I have one more slide, expected value. We're going to do some expected value. Expected value is really easy. It's just n times the success probability. So n times, if the success is 50%, so n times 50%. And this is the expected value that we should get in this. Really easy to find. Again, I'll show you that with our example. All right. So a candy company produces bags of strawberry and vanilla flavored candies. Okay, 65% are strawberry, which then mean, of course, the rest is vanilla. What's the probability that in a bag of 10 candies, there's at least 4 strawberries? All right, so a success is 0.65, so that means the failure would be the opposite of that, or 0.35. Now, we have 2 ways to figure this out. We can either find the probabilities of having exactly 4, 5, 6, 7, 8, 9, and 10, and then add those all together. Or we can calculate the probability of having exactly 0, 1, 2, or 3, and then subtracting that from 1. So we can do it either way, and whichever way obviously is easier is the one we should do. Now 4, 5, 6, 7, 8, 9, 10, that's 7 different possibilities that we're going to have to find. This one here is only going to be 4. So if it's only 4, I'm going to take the second option. I'm going to find the opposite and then just subtract it from 1 because it's got to, again, always add up to be 100%, right? So because it says at least 4, you're talking about 4, 5, 6, 7, 8, 9, 10. This is really what we want to find, probability of the first one here. But if we can sneak around and do 2, do a little less work, subtract it from 1, that will give us that answer to 1. All right, so let's do this. So here we go. These are our different probabilities. So probability of 0 is the combination of 10 things taken 0 at a time. So how many successes are we having? We have 0 strawberries in this batch. And so 0.65 times 0 to the 0 power and 0.35 to the 10. How many successes we have? We have 0 successes and 10 failures. We put that in our calculator, we should get this value right here. Not a very high one. Then probability of having 1 strawberry. 10 things taken 1 at a time. 0.65 to the first and 0.35 to the 9th. Notice these numbers here, 1 and 9, should add up to be the total number of possibilities. 0 and 10 add up to be 10. We have 1 success and 9 failures in that bag. What about the next bag? 10 things taken 2 at a time. So it's 0.65 squared and 0.35 to the 8th. Again, here's our number, 0.0043. And the probability of 3 is here, 0.021. So we go ahead and add all of our values up, the 0, the 1, the 2, the 3, and we get 0.0258. Now that is a decimal, so we need to make that a percent. And again, we subtract it from 1 to get 0.97, move it over to places 97.4% of the time, they'll have at least 4. Okay. So the probability of at least 4 is about 97.4%. And that's how we can use binomial probabilities. What is the expected number of strawberry candies? What do we expect to be in the bag? Well, that's pretty easy. We take that 0.65, times it by how many? And remember, we have 10 candies in a bag. So n/s, so 10 times 0.65. So we should expect 6.5. So either 6 or 7 should be what we should get in each bag. So that's why some of these values were so low, because we should expect 6 or 7 in a bag, not 0, 1, 2, or 3. Are they possible? Absolutely. Very rarely, but they are possible. So our expected value is 6.5. All right, let's try another one. A former study assessment suggests that 75% of all middle school teachers are women. If a randomly selected school employs 10 teachers, what's the probability that at least 2 male teachers are employed at the school? So we can either do number 1, which is add up the probability of 2 to 10, or we can subtract the probability of 0 to 1 from 1. Well, obviously, the 0 to 1 is significantly less work than doing 2 to 10. So we're going to do the 0 to 1 and subtract from 1. So the probability of 0, so this would mean that there are 0 males. So the probability of success for a male, notice the difference here. This is 75% are women. So how many are men? The success is 0.25. So the failure is 0.75. So 0 males, that happens like 5.5%. Now when we do it with 1, we get up to 18.77%. Again, add those together, subtract from 100, and we get 75.6%. How many should we expect? Well, 0.25 times 10, or 2.5. So 2 or 3 male teachers is what we should expect if this data is correct. All right, there are 5 contestants on a game show. Each contestant has a chance to choose 3 doors, one of which has a car behind it, to determine the probability of 3 contestants winning. So there are 5 contestants, so we want 3 successes. Each success is 1 out of 3. There's only 3 doors, so they get 1 out of 3 chance, so 33%. Failure is 67%. So 3 successes and 2 failures, giving us just 16.1%. Notice I didn't have to do 4 and 5 because it didn't say greater than. It just said the probability of 3 contestants winning. So they only just wanted the one value. So we went ahead and just found that one value, plugged it in, and there's our answer. We found a probability of the number of girls in a family of 4 to be as follows. 4 girls was 6%, 3 girls 25, 2 girls 38, 1 girl 25, 0 girls 6 again. Describe the binomial probability distribution and the shape of the distribution. So graph it and then describe it. So we're going to go ahead and put the values on there, and we do the graph. Now notice this graph. This graph is a normal graph. All the high values are in the middle, and it's equally distributed on both sides. This is a normally distributed graph. It's not skewed one way or another. What about this one? A little bit of review again. So we have a value over here, and we're missing these values over here. So we're missing the positive values. So it is positively skewed. All right, another couple formulas here. So how do we use this normal graph with a binomial distribution? Well, remember with the normal graph, we need our x-bar, our mean, and our standard deviation to go ahead and do any kind of things with our normal graph. So we need to know the middle and then how far each line is, each standard deviation. So we have new formulas. So x-bar is just the same as the expected value, n times s. And our standard deviation is the square root of n times s times f. Kind of putting that all together. A little bit of a weird formula, but it does work out, obviously. All right, so let's see how we can use this. According to an online poll, 64% of middle-aged graduates feel that their college years were the most exciting. So Bernardo conducts a survey for 300 random middle-aged adults with college degrees. What's the probability that no more than 175 of the responses will agree? So we need to take a look at what we've been given. We've been given N being 300, and S is at 0.64. So F, again, we have to subtract from 1, is 0.36. So we're going to use this normal distribution to approximate the different values. So we have to find our different values. So we have to do our X bar and our standard deviation. So X bar is N times S, so 300 times 0.64 or 192. We also have to do our standard deviation, plug those values in, take the square root of it, and we get about 8.3. All right, so how does that work? Remember, this is our standard deviation chart, our probability, our normal distribution chart. I took this from the section earlier this week. And the middle is 192. That was the mean. The mean is 192. Now remember, we go one standard deviation, or 8.3, in each direction. So this is 183.7 and then 175.4 for this value here. This one is 203. Now we want to be less than 175, which is basically this value right here. It's a little off, but we're just going to call it that. So what are the areas that are less than this 2% and this 0.5%? So we got to add those together for an answer of 2.5%. So that's how we can use our normal distribution with our binomial distributions to come up with some percentages. Let's try another one. According to a city poll, 74% of students enjoy a walk in the neighborhood park. City planner conducts a survey of 200 random students. What's the probability that more than 154 of them will respond with an agreement? So we're looking for that 154, which bar that is. So N is 200, so success is 0.74, so failure is 0.26. So we need to find the mean, and we do that by doing our X bar, so N times S, so just 200 times 0.74, that's 148. And then our standard deviation is NSF, so multiplying all those together, take the square root, gives us 6.2. So 148 in the middle, and now I'm going up, 6.2. We get 154.2, which is basically that 154 value that we want. We want the probability greater than 154. So we're talking about this line right here and all the numbers that are bigger than it, 13.5, 2, and 0.5, adding up to be about 16%. And that's what I have for you today.